Every quantum algorithm begins with a problem. Today, we're faced with a mysterious black box. We don't know how it works inside, but we do know it always behaves in one of only two possible ways. In quantum computing, this mysterious black box is called an oracle. We can give it inputs and observe its outputs, but its internal function remains completely unknown. The oracle is guaranteed to belong to one of only two categories. It either produces the same output for every input, or it produces an equal number of zeros and ones. A constant function is the simplest case. Every possible input always produces exactly the same output. It can be all zeros or all ones, but it never changes. A balanced function divides its outputs equally. Exactly half the inputs return 0, while the arrangement may differ, but the balance always remains. These examples look simple, but imagine millions of possible inputs instead of just 4. How many times would we need to query the oracle before we could identify its type with complete certainty? A classical computer has only one option. It must keep testing different inputs. Every new query reveals a little more information, but never the complete answer. Even after many successful tests, uncertainty remains. The next unseen input could completely change our conclusion. Consider these two functions. After checking the first few inputs, both appear identical, yet a single unseen value can completely reveal their true nature. In the worst case, a classical computer may need to examine more than half of all possible inputs before it can guarantee whether the function is constant or balanced. As the number of inputs grows, the required classical queries increase exponentially. But quantum computing approaches this challenge in an entirely different way. Instead of checking one input at a time, the Jozsa algorithm uses quantum principles to extract the answer in a remarkably efficient way. Let's build the circuit and see how it works. The algorithm starts with 2 qubits. The first is initialized to 0, while the second begins in 1, ready for the quantum operations ahead. Hadamard gates create superposition. Each qubit now exists in multiple possibilities at once, enabling quantum parallelism. Unlike a classical computer, the quantum state doesn't test inputs one by one. Through superposition, every possible computational path reaches the oracle together in a single. The oracle doesn't just return outputs. It encodes the function into the qubit's phase, revealing information through quantum interference. The qubits pass through another Hadamard layer. Their encoded phases interfere, revealing the hidden structure of the function. The remarkable power of the Jozsa algorithm lies not in measuring every possibility, but in carefully shaping interference so the final measurement reveals answer with single query. The algorithm's real power lies in its probability amplitudes. Like waves, they can combine, reinforce, or completely cancel one another. When identical waves meet, they reinforce each other. This is called constructive interference, making certain outcomes far more likely to be measured. Opposite phases behave differently. They cancel each other through destructive interference, removing outcomes that carry no useful information. Each input contributes a quantum amplitude. Together, these amplitudes create the interference pattern that determines the algorithm's final result. Constant functions reinforce the amplitudes. Balanced functions cause them to cancel, producing two completely different quantum outcomes. One oracle query. One measurement. The interference has already revealed whether the function is constant or balanced. The difference is remarkable. While a classical computer explores many possible paths, the quantum algorithm reaches the answer through a single elegant computation. In the worst case, a classical computer may require over half the possible queries. The Jozsa algorithm needs only one. Although this problem has limited practical use, the algorithm proved that quantum computers could outperform classical computers on specific computational tasks. It became the foundation for future breakthroughs, inspiring more advanced quantum algorithms that continue shaping modern quantum computing research. Its greatest contribution was simple, yet revolutionary. It showed that quantum mechanics could transform the way we solve computational problems. The Jozsa algorithm marked the beginning of quantum algorithm design. And from this milestone, the journey toward even more powerful quantum algorithms truly began.